Today I'm going to start by reminding you of some things about exponential functions that we have already covered in a previous video, and then we're going to focus on the most typical types of situations that are modeled by exponential functions. We've already mentioned them as well, but I want to focus on what's good and what's bad about using exponential functions to model those situations, and then talk about another type of function that can also be used to model some of those things that in some ways is better than using exponential functions. So let's begin by making a summary of the important things that we know about exponential functions. That is the defining characteristic of exponential functions. The rate of growth is directly proportional to the current value of the function. The rate of growth of a function is the derivative of that function. Here is some notation for the derivative of a function so that we can put that into equations if we want. So the defining characteristic of exponential functions is that the derivative is directly proportional to the function itself. Here is that same sentence written down with notation as an equation. I don't particularly like this symbol for something being directly proportional to something else. So here it is written down in a different way. Something is directly proportional to something else when it is a constant multiplied by that thing, right? So the derivative of the function is equal to k times the function itself. If your function has that, that means that it is exponential. With this constant k here, well, if that constant k happens to be the very special number 1, and instead of being directly proportional, we are just saying that the derivative of the function is equal to the value of the function, that is what the number e represents. And then if the constant happens to be a different number k, it just becomes e to the power of kx, which, using the rules of exponents, becomes a different base. So the important thing that we just reviewed is the fact that exponential functions appear as solutions to this equation. Now there is another vocabulary that I didn't mention in that video because this was the only one that we were looking at, but this is called a differential equation. Today I am mentioning it because we are going to look at another differential equation besides this one. But before we do that, here is a little bit of another video where I explain just what a differential equation is. And don't worry about the scary picture just yet. I will explain that in a minute. So first of all, when we say equation, we are used to thinking about things like this, for example. It's an equality that depends on a variable, and we are trying to find the values of the variable for which that equality is true. When we're talking about differential equations, of course, there needs to be a derivative there. That's why it's called differential. But the more important thing that you need to remember about it is that the solutions that you are looking for are not values of x. So x is not the variable in this equation. What you want to find is functions. F of x is the variable here. We're trying to find functions so that this equality is true. The derivative of the function at any point is the value of the function plus x in this example that I'm working with. And just like in the traditional equations, you don't need to have just one solution. In the differential equations, you're usually going to find infinitely many solutions. It is a family of functions, all of which satisfy this equality here. Which brings me to the picture that we are looking at. This is just the coordinate plane. You have the horizontal variable x and the vertical variable y. And at each point, you are also seeing an arrow. This arrow represents the derivative of the function that one of these functions that are solutions to the equation, the derivative that it needs to have if it passes through that point. Because like I said, it's a family of functions. It's not just one function. So it's going to turn out that in every point of this plane, there is one of the solutions is passing through that point. And it is passing with this slope. So this picture is called a slope field. For example, if it passes through this point here, then it will pass with this tangent line And if it passes through this other point here, then it's going to pass with this tangent line. These are not necessarily the same function because there are infinitely many functions in this family, but for all the points, the function that passes through that, the solution to the differential equation that passes through that point, needs to pass with that tangent line indicated in the slope field. So the first exercise that I like to have my students do when we study this is to just try to sketch by hand. You'll have this image printed on paper, then you choose on the left-hand side here a point to start with, and just try to sketch a function following these arrows. You can sketch many different ones depending on which point you choose to start. And I think it's important to do this exercise with students at the beginning of studying this topic of differential equations, because it turns out that doing this is very intuitive for a lot of people, but for others, not so much. Other people get confused as to how do I know which way to keep sketching. It's something that you get used to after you do it a bunch of times, so it's worth spending some time doing that, because this is really what a differential equation is. It is a function that is trying to go somewhere, but it doesn't have the freedom. It has to follow what the equation tells it that the derivative needs to be. And that is changing at each point. When you move a little bit, then there is a different derivative, and then you have to follow that other direction, and so on. So there are a bunch of different pictures here in this file. Some of them are really crazy. Let's try to do this one. I'm going to start with a point here, follow this arrow. Something that is important to mention as well is that we are seeing a finite number of arrows in the picture, but conceptually, all points have an arrow, okay? And so if you are at a point here where there is no arrow at that exact point that I'm sketching right now, you can kind of just look around and see what the other arrows around it are doing, because it's not going to be a crazy difference. So in this one, I have an arrow pointing up here and an arrow mostly horizontal there. So something in between. It's still going up, but not as strongly as the arrow under it is showing. So you kind of average out the arrows that you can see around it, because this really is a continuous field of arrows. Let me just change the notation a little bit for my differential equation. I don't want to keep calling it f of x like a function just because that is clunky notation. I want to instead use just y, because y equals f of x is how we draw functions. And the important thing here is that the differential equation gives us a rule that connects the derivative of the function at each point, which are the arrows, to the coordinates of the point, which are x and y. In the case of this example, this is the relationship. It's that the derivative needs to be y plus x. This happens to be the example that we are looking at right now. But of course, the right-hand side of this equation is going to change with each example. And you should notice that this equation for exponential functions fits perfectly into what I was just saying in that other video about differential equations. It is an equation, it has a derivative, and the thing that we are looking for here, the solutions to this, are going to be the functions, which in this case would be the exponential functions. Now I'm also going to rewrite that in the other notation that I mentioned, because I think that that highlights why this particular equation is going to lead to a function with the features that we know that the exponential function has. Most importantly, the horizontal asymptote where y equals 0. Because when y is 0, that is everywhere in this horizontal axis here, y is 0, so that means that y prime also needs to be 0. The derivative is 0, which makes the function horizontal. And the fact that it's not exactly 0, but just very close to 0, means also that the function is not exactly horizontal, but it's growing very, very slowly until it speeds up. And not only on the axis will the derivative be 0, making it the asymptote, but also y prime is equal to y everywhere. So the higher up you go, the bigger your y, your function is wanting to go up faster. This is the slope field, like I was just showing you in the other video. And for negative values of y, the derivative also wants to be negative, so those would be decreasing functions. And the function that we're going to draw here needs to follow all of these arrows. It's going to be kind of like that. Now, it didn't need to be exactly this function that I drew here, because a differential equation doesn't just have one solution, but a family of solutions. There is a solution passing through each point in the coordinate plane. So basically, any exponential function with the horizontal asymptote at 0 is going to be a solution to this equation. It can be because it takes longer to start increasing. It can be because it's upside down. It can be because it's going the other way. But the horizontal asymptote is always going to be at 0, because y equals 0 is the value that makes the right side of the differential equation equal to 0. And therefore, the left-hand side, which is the derivative, also has to be 0 here, which makes it the horizontal asymptote. Now, if we wanted a horizontal asymptote at a different value, like here, for example, at y equals 2, then we would need a slightly different differential equation, like this one that has the right-hand side equal to 0, not when y equals 0, but when y equals 2. Because now when y equals 2, this is just 0 times k. So at y equals 2, the derivative of the function is going to be 0, which gives the solution a horizontal asymptote at y equals 2. Now hold that thought for a little bit. I am going to go back to talking about differential equations later in this video, but now I want to go back and talk about some of the situations that are usually modeled by exponential functions and why that is a good model, why that is a bad model, like I said that I was going to do. Those will be the typical types of situations where the derivative of the function, the rate of growth of the function, is proportional to the current value of the function. And the first example is population growth. When I say population growth, it can be humans, but it can also be any kind of animal. So if you start out with more rabbits, then they're going to make more rabbits than a smaller group of rabbits would make. So the number of new rabbits, which is the growth of the function, is proportional to how many rabbits were there in the first place making those rabbits. So that is a perfect example of exponential growth. And as a consequence of that, you're going to end up having something growing really, really fast because it's exponential. So that is why population growth is kind of a complicated topic, because you end up having rabbits taking over the world or something like that. I will talk about the rabbits taking over the world in a little bit, but first I want to mention another reason, a simpler reason why you could say that exponential function is not a perfect model for population growth, and that is because the exponential function, like any function for that matter, is something that goes from the real numbers to the real numbers. So both the domain and range are subsets of the real numbers. The real numbers are continuous, but this is not a continuous situation that we are modeling. This is a population. So you can't have half of a rabbit, you can't have pi rabbits, you can only have 1, 2, 3, 4, 5 rabbits. So this function will never represent exactly the reality of the number of rabbits that you have. But that is kind of what the word model means. It's not an exact representation of reality. It's a representation that is simplified enough to make calculations manageable. So in other words, calculating as if it was possible to have half of a rabbit makes it so that we can use this model to make predictions about our number of rabbits in the future. And that is what we want our models to do, basically. We want them to be useful. So in order to be useful, we need to be able to handle them. And discrete things tend to be a lot more complicated to handle mathematically than continuous things, which is the whole reason why we model situations with continuous functions, regardless of whether that is the reality of the situation or not. And money in the bank grows exponentially as well, because the interest rates that the bank pays you is not a fixed amount of money per month. It's not like I'm going to give you $100 each month. No, it's a percentage. It's an interest rate. So they're going to see how much money you have, calculate a small percentage of that, which is proportional to the whole, and then give you that much again. So at first sight, money doesn't have the same problem as the rabbits did, because you don't necessarily need to have an integer number of dollars. They are more divisible than that. So maybe your bank account has $2,345.67. So that is not an integer, because the 6 and the 7 are decimal places. And it makes it a little bit smaller, but it is still the same problem. Money is still discrete, except that the thing that can't be broken into little pieces is not the dollars, is the cents. So because it is a smaller thing, maybe the difference between the model and the reality will be smaller, will be less noticeable. But the critical issue is still there. The model is continuous and the reality is discrete. But there are also a couple of typical situations that I want to mention that are decreasing functions instead of increasing. So the first example of a decreasing exponential function that you're going to see a lot is radioactive decay. So you have a radioactive substance, I don't know, it's uranium or plutonium or something, and you know that that stuff decays, right? They emit particles or whatever, I don't know physics, but as they do, those particles consume its mass. So the mass of radioactive substance that you have tends to get smaller over time, and depending on the substance, that is going to take a long time, but the rate at which that happens depends on how much of the substance you have. If you only have a tiny little bit of radioactive substance, it's only emitting a small amount of particles, so its mass is decaying slowly. But if you have a huge amount of radioactive substance, then it's going to be emitting proportionally more particles, and more particles are going out, so it's decaying faster, so it's directly proportional to the current mass, so it is exponential. So when we were talking about population, we needed the natural numbers because it was a whole number of rabbits. And then we were talking about money, which also was a discrete thing that couldn't break the cents apart. But when you talk about the mass of a substance, it feels like it is a more continuous thing, because mass is measured in kilograms, and you don't need to have just 1, 2, 3 kilograms, or even just a limited number of decimal places of kilograms like you do with money, in which you only have 2 decimal places for the cents. No, kilograms can be like 10 to the negative 17, which is really, really small, and it can go as small as you want. So I feel like maybe this time the model is continuous and it's actually modeling a thing that is continuous in reality, but not really, because the radioactive substance, like any substance, is made up of atoms, and at some point, it can take thousands of years, but at some point, the last radioactive atom in that thing is going to decay, and then you're going to have 0 radioactive atoms in there. So that's not really an asymptote. That is just a function that will be constant and equal to 0 from that point forward. So again, our problem is getting smaller and smaller and smaller, from 1 rabbit to 1 cent to an individual atom, but we are still carrying over the same problem of using a continuous function to model discrete situations. And the last of the 4 traditional contexts that I want to tell you is coffee. Specifically the temperature of the coffee, which is also decreasing. It has a horizontal asymptote on the right side in the end, because your coffee is not going to freeze no matter how long you take to drink it. It's just going to become the same temperature as the room, which is why this particular exponential function does require the vertical translation that gets the asymptote out of the axis and puts it here somewhere else. Now, I don't know enough about physics to have an opinion about whether temperature is a thing that is continuous in reality or not. Of course, we are still going to be using the continuous models for all of these situations, no matter what. But the thing is that temperature is about the motion of particles, how fast are they moving. And even though it is a huge number of particles, my cup of coffee is still made up of a bunch of particles, which is an integer number of particles. But then there is the thing about the speed at which they are moving. And it feels to me like speed can be any number, and that's where the amount of physics that I know is over. I don't know any more than that. So these are things that are really interesting to talk about. To what extent the mathematical models that we use are actually representing reality in a precise enough way, in a way that keeps the main features of how things actually work. But that is not really the direction in which I am going with this right now. I want to go back and talk about the infinite rabbits. Remember, we mentioned that the exponential function grows faster and faster. It's definitely going to infinity. It can never reach infinity because infinity doesn't exist. But it means that however big a number of rabbits that you can imagine, at some point your model is going to say that that's how many rabbits you have. And it doesn't even look like it's going to take that long because it's growing very, very fast. But that's when the rabbits take over the world. How many rabbits would it take? Trillions of rabbits? Quadrillions of rabbits? It doesn't matter. The exponential model can get you there in a finite amount of time. So in that sense, that is a problem with that model. It only works up to a point. After that, there is a natural limitation on the number of rabbits that even fit on the planet that your exponential model is just not seeing. And that is a much more important issue than the discrete versus continuous thing that we were just talking about. Not if you're only going to use your model to predict the number of rabbits a short amount of time from now, but if you want to use it for a long period of time, then you're going to need another model because that one is really not good enough. So here's the thing. The exponential model has this horizontal asymptote at y equals 0, but the problem that we've been talking about tells us that there is a maximum number of rabbits that there can be ever. So it's a number on the vertical axis that this model shouldn't be able to cross because you can't fit more than those rabbits in the planet. So that looks like we want a second horizontal asymptote right here. You can still see the original function behind it, but that is the effect of the second asymptote. Both functions start out looking pretty much the same, but then at some point they separate from each other, and the new function is going to stop here at the second asymptote. And that's when we're going to go back to talking about differential equations. Because this differential equation is making a horizontal asymptote at y equals 0, because if this is 0, then the right-hand side is 0, and there is the horizontal asymptote with derivative 0. But this differential equation is, for similar reasons, making a horizontal asymptote at y equals 2. And now we want a function that has both. So that's why the differential equation is going to look like this. This right-hand side here is equal to 0 both when y equals 0 and when y equals 2. In between these two values, the derivatives are going to be positive. I mean, assuming the constant k is positive. If it was negative, it would just be the other way around. And outside of the two values, it's negative. This is just a very rough picture of a slope field that I'm drawing here. And the reason why it's going negative, positive, negative for the derivatives here is because this right-hand side is like a quadratic function where the term in y squared has a negative coefficient so that the function is positive between the two zeros and negative outside of the two zeros. So there you go. Between 0 and 2, it's positive, and outside, it's negative. So now I'm going to solve this differential equation. In fact, I'm going to show you a part of a different video where I've already solved it. But before I do that, I'm going to manipulate this expression a little bit so that it looks exactly like it does in the other video, okay? First of all, 2 is an example here, so I'm going to change that 2 into a constant. And just to look exactly like it does in the other video, I'm going to change the name of the variable from y to b. This right-hand side here, I'm going to divide by n inside of the parentheses and multiply by n outside, which doesn't change anything. Well, it does change the way that it looks, which is exactly what I'm trying to do. This part here, I'm going to rewrite as 1 minus p over n. And that constant n times k over there, I am just going to rename it to simply call it k. Now, I realize that this is a video in which 20 minutes ago I was telling you just what a differential equation is, as if you've never seen it before. So I know that you don't know how to solve differential equations, okay? Or at least I'm not assuming that you do. But don't worry about that because I'm going to talk you through it while I'm doing the example. There are many different techniques for solving differential equations, but for this one, we are only going to need the very first one, the simplest one, which is called separation of variables. Separation of variables happens when you can separate on either side of the equation just the independent variable on one side and just the dependent variable on the other side. Over here, I think it was dp dt, which, by the way, this notation is more convenient for separation of variables than the p prime notation. And so the independent variable t doesn't even appear on the right side of the differential equation. This k and the n are constants. So it doesn't really matter to which side of the equation you leave the k because it's just a constant. But that is what I meant by putting the independent variables on one side and the dependent variables on the other side. That means including when it appears on the dt and the dp. So yes, this is pretty much an abuse of the notation because dp dt was never a fraction to begin with. So if you find it strange that we seem to have multiplied both sides of the equation by dt here, you're right, this is strange, but it's exactly the reason why the notation dp dt for derivative is so convenient for this type of differential equation, because you get to act as if it was a fraction, and it's really not that crazy because when you think back on the meaning of derivative, dp dt is the slope of the tangent line, which I've drawn in red here, and slope is rise over run. So if you are going to use dp over dt as a notation for the slope, then it makes sense that dp is the rise and dt is the run, because p is vertical and t is horizontal. And of course, I should be saying the same things for y and x as well. It's just that in this particular example, it happened to be p and t. So anyway, the notation does make a little bit of sense, and it is very convenient because right now you can just say that you're going to integrate both sides. And that's why I said that this type of differential equation is the easier if you are very comfortable with integrals, because you have to be able to look at that one and identify that that is partial fractions. This video is about differential equations, not about how to solve integrals, so I'm not going to go over the details here. You can use your favorite strategy to figure out the values of a and b have to be in order for this plus this to be equal to that. It turns out that a needs to be 1 and b needs to be 1 over n. So when you integrate that, you get ln of p here, and this other term over here, I've used a substitution u equals 1 minus p over n in this part. And you don't need to put the plus c over here, okay, because you're doing the differential equation. You're going to have two integrals, so it's enough to have one integrating constant. I'm going to do it on the other one because it's simpler. Because the thing is that if you have plus one constant over there and plus a different constant over here, you might as well subtract that constant from both sides of the equation, and then all you have is one constant on this side, which was the original one here minus the one from over there. So you just call that the constant for your differential equation. Yeah, so there's another thing that you actually need to be very comfortable with in order for us to be able to call this thing easy. Like I said, that the separation of variables was the easy case of differential equations. Which is that you still need to solve this equation, right? What you want is to find p of t, and p is not really isolated yet in this equation, but we're going to use logarithm rules and properties, and we're going to be fine if we're very comfortable with that stuff. So I've put both logs together, and now this fraction is kind of bothering me, so I'm going to multiply by n on numerator and denominator in there. Now, of course, we want to get rid of that log, so the next step is going to be to say that the big fraction is e to the power of this thing. And please notice here that this is a very common type of mistake that people make on this step, is that you know that there needs to be the plus c that we were just talking about, plus c, and then people just assume that the plus c is always going to be plus c. But it's not really, because now it is in the exponent. It is not e to the power of kt and then plus c. The plus c actually needs to stay in the exponent, which is the common mistake that I was mentioning. Sometimes people let the plus c fall down over here, because the proper moment to include the plus c in the solution is here. It's when you do the integration, because it's integration that creates this constant. After you have integrated and a constant is already here, the rest of this process is no different from solving an equation. So you still have to follow all of the same rules that you used to when you learned how to solve equations in the first place, which includes the fact that when you do one operation to one side of the equation, you need to do the same operation to the other side of the equation. So it is the kt plus c, the whole side of the equation, that is getting into an exponent of the number e. So this is the correct way to write it. And in fact, this next step you don't actually have to do, but I like doing it. So I see a plus in an exponent, I'm going to split it up into a product of two powers of the same base. And now e to the power of c, because c is a constant in this situation, the only things that are variables are p and t. So c is a constant and e is also a number, so e to the power of c is also a constant. I want to erase the e to the power of c and just call it a letter, which is still going to be a constant. And the pretty thing here that people sometimes like to do is that you don't actually have to change the letter. You can take away the e to the power of c and call it c. It is a different value of c than the one we had before. But this is, and you have to be careful with it, because if the c is appearing in multiple points in the equation, please don't do that, because one letter needs to have one value in the whole equation. But since here it was only appearing once, then I get to do that. I get to change the name of my constant, but it's not the same thing as the mistake. It's not that the c was on the exponent and I accidentally let it fall down, because it is now multiplying. It is not plus c, it's times c. So now moving on with the solution of the equation, I'm just going to do the traditional steps that I do when I have my variable that I'm trying to isolate in both sides of a fraction. I've multiplied both sides of the equation by the denominator, and now I'm going to do the distributive. And now I'm really just solving a linear equation, right? I'm going to put the p's over there, factor out the p, and divide both sides by that thing that is multiplying p. So we've just seen that this function is the solution to that differential equation, and this is the logistic function that we've been looking for this whole time. But it's often not written down in this way. So I'm going to do a little bit manipulating again in order to get it into the format that you will usually see it written. So first of all, I'm going to divide the numerator and denominator by e to the kt. Now I'm going to divide them both by c. I'm going to rename this constant n up here into L, and this other constant here, the number L over c, I'm going to again rename to the letter c. I know it feels kind of weird when I rename something that has a letter into the same letter, but these are just numbers anyway. You're not going to be dealing with both of them at the same time, so it's okay if they have the same name. Just switch the order of these two things being added here. Let's make this into a function of the independent variable x instead of t, and get rid of that name p over there. Let's call this f of x. And this is the logistic function in the way that it is written in the formula booklet for the AI high-level course, which is the only one of the 4 IB math courses that has logistic function as part of its content. Now, of course, it was an interesting trick, this idea of setting up a differential equation to have the two asymptotes that we want, and then basically just seeing what happens, because this is all that we did, right? We started from we want two asymptotes. We told the differential equation exactly the fact that we wanted two asymptotes and nothing else. And then the whole logistic function just almost magically came out of there. But there are a couple of important observations to make about that as well. First of all, the logistic function is not the only function that has two asymptotes. As a simple example that you should recognize, the inverse tangent function also has that feature and is not the logistic function. It's not even just a stretch of a logistic function, it's a different function. And another comment also is that when you look at the slope field it's going to look like the logistic function if you start at a point that is between the two asymptotes, because then it's doing everything that we've been trying to make it do, right? It slows down here. It came from arrows that have smaller slope over there. But if you started here, for example, you would get a completely different function. You would still have it slow down close to the asymptote, but over there it would just go up forever. Or here, for example, also slowing down at the asymptote here and growing faster and faster on the other side. So they look like exponential functions. But the most important observation is that even though the trick was very cool, you cannot get carried away and think that you can do whatever you want with the same kind of trick. It's not like you can just think up features of a function and then the differential equation that you write from those features will magically give you a function that does what you want. In some simple instances, this might work like it did in this case, but it's a matter of luck. It's clearly not going to always work. As a very simple example, if you just put a third factor here, now you are also looking at making the derivative equal to 0 at a third point, which is y equals -2, and that's going to change the slope field, but you're never going to get a function with 3 horizontal asymptotes because that's impossible. A function can only have 2 at most, one on the left and one on the right. Here, the shape of the functions that you get as solutions to this differential equation are basically going to look like logistic functions as well. It's just going to depend on the point where you start. So these are some of the options that you would get. And now that we know everything that there is to know about logistic functions, I want to go over a couple of interesting examples. I have been using the population of rabbits example to explain why the logistic function is important as a model, because it is the most traditional situation in which you will see logistic function being used. But of course, it's not the only possibility. Basically, anything that has two asymptotes you can think to model with a logistic function. And I'm going to start by showing you this one, which is one of the things that students really like to use as examples for studying linear correlation. This is countries' GDP per capita and life expectancy. And there's a lot of variations on that pair of variables that students really like to use for linear correlation. The idea being, in this case, to show that the richer the country, the longer the people live, which initially makes sense when you say it that way. So let me go over what I did in this example here. First of all, here are my sources for GDP per capita. I'm using this website. And for the life expectancy, it's this other website here. Now, both lists of countries were really big, almost 200 countries. And the problem that I faced was that they're not exactly the same list. Mostly it's the same list, but when I copy the data from both websites into a spreadsheet and I try to match country by country, there are some countries missing from one list or the other, usually very tiny countries that one of them considered and the other one did not. And there were also some instances of countries that were spelled slightly different on both lists. So because of that, I ended up deleting them because it would just be too much work to try to match the lists perfectly. And it doesn't matter. Even though I did it this way, I still ended up with a list of 170 countries, which is a big number for data analysis. So that's okay. And when I plotted these numbers with the GDP per capita on the independent variable and life expectancy on the dependent variable, this is what I see. So the naive student who was trying to do linear correlation with this is going to be disappointed because it only works kind of here. For the poorer countries, which I guess you could argue is most of them, judging by the number of points on the graph, but yes, of course, our intuition makes sense. Richer countries, people live longer, and the student who is looking for a linear correlation will apparently find it because that looks kind of linear, at least looking from this distance, even though there's a bunch of outliers down here. They are very few, so I don't think they would interfere too much in the line of best fit. But all of these guys here, they would interfere with the line of best fit a lot. In fact, if you try to do that, you get a line that is kind of like this, and bears absolutely no resemblance to what you wanted to see in the graph, you do see a very strong pattern by looking at the graph, but that pattern is not linear. It goes like this. And the interesting interpretation to draw from that is that yes, more money means people live longer, but this horizontal asymptote means that there is also a biological limitation on how long people can live. So after a certain amount of money, which subjectively you could interpret up to here or up to here, then yes, having more money makes the country have a longer life expectancy, but it doesn't really go more than, I don't know, what is that, 80 something years old? So I'm just sketching this curve that looks like the end of a logistic function. I'm doing it by hand according to what I'm seeing with my eyes. But if I really want to do a logistic regression on this scatter plot, of course, if you're doing an IA, that is your best option. But unfortunately, Google Sheets doesn't do logistic regression. It does linear regression and exponential and a couple of others, but not logistic. So when I got to this point, I decided to use my TI-84 instead. But the problem with that is that I have a list of 170 countries, and I really don't want to type that again into my TI-84. So I decided to make a random sample out of these 170 countries to just make a smaller list that still represents that. And I know that things like regression and random samples are not the kind of content that you are expecting to see in this video. But when I start working with examples, it's inevitable for me to get into a frame of mind of like, how would I make an IA about this? And that's how you write IAs. You draw from all the content that you know and use it when the situation calls for it. So now I want a random sample out of these 170 countries. I don't want to choose which countries. I don't want to take the most famous ones. I don't want to do categories and do stratified sampling. That is too much work. The random sampling works best. The only thing that I want is to shorten my list, make it smaller. So I have 170. I thought to myself, well, maybe 20% of that would be enough. 20% of 170 is 34. So that I'm okay with typing. So what I did in the spreadsheet is that I created another column where I asked it for a random value from 0 to 4 in each row, because then you have a 20% chance of getting a 0, 1, 2, 3, and 4. So you expect that like 20% of them will be zeros. And again, I'm talking about theoretical probability versus experimental probability. I'm talking about the expected number of results. This is all content from the course that has nothing to do with logistic function, but I'm writing an IA in my head right now, so I can use anything that I want. So I picked these random values. I ordered the spreadsheet by the values. So I took all the ones that had selected 0. It was not exactly 34, it was 33, but that's fine. So now I had a list of 33 randomly chosen countries, and the scatter plot for those 33 countries looks like this. It's pretty much the same, but with fewer points. So I can still see kind of the logistic function that I want here. And just in case you're not seeing this, I'm calling this logistic because I'm imagining that it continues the other way, okay? But then I typed the 33 values into my TI-84. I asked it to do the logistic regression, and this was the answer. So notice that in the TI-84, the names of the constants are different. We have a C here, an A here, and a B here, but that, of course, doesn't matter. And then it gave me these values. I asked it to plot the function from the regression together with the scatter plot from the data. It looks pretty okay, I guess. Visually, it could be better. I was hoping it to do this, but I should trust the technology instead of my eyes. Should I? I don't know. That's a discussion for another day. But anyway, where is the rest of the logistic function? Does it actually look logistic? So I changed the window in which I was plotting. And yeah, it looks exactly like a logistic function, of course, even though we don't have any data points on the left. Data points on the left would not make sense because it would be negative values of GDP per capita. But I still wanted to see this function laid over the original graph with all of the 170 data points. I can't do that in the calculator without typing all the points. So instead, what I'm going to do is to take the function with the values of A, B, and C that the calculator gave me, and I'm going to type it into GeoGebra, where first I have placed the original scatter plot in here. I've made it a little bit transparent so that we can try to match the numbers from the scatter plot with the numbers from the axis in GeoGebra, and it's scaled down by 10, but that's easy to fix. Same thing is happening here on the horizontal axis, where the 2 from GeoGebra represents the 20,000 from the data. And I'm not going to show you exactly how to do that today, but it has to do with these points A, B, and C here that you can put into this tab. And then as you move them around, you visually match one number with the other number. That's important because now I'm going to type the function. And when I do that, I do have to think about the vertical stretch and the horizontal stretch because of the different scales that I was just mentioning. And here's another good thing for our hypothetical IA. Now we are adding stretches, vertical and horizontal graphical transformations. So that's good. And as I typed the function, put it over the scatter plot, it looks like this. And again, it's fine, I guess. It doesn't look amazingly good or anything. It's a little disappointing that the asymptote is at approximately 80 years old, but you have all of these points with life expectancy way above. Like this one is 86, I think. But you know all the reasons for that, right? It's just the way that regression works. So anyway, that was one example. And then the other one that came to my mind was the fact that there is a well-known belief that the speed of computers like doubles every such amount of time. I don't know. And doubling in each specified amount of time is the classic definition of an exponential function. So are our computers getting exponentially better as time goes by? By better, I mean faster. And that is not obvious, okay, because it feels to me like even though we have been observing for decades, ever since computers were created, that this is what's been happening, this exponential growth. But on the other hand, computers are physical things. There's a limit to how small you can make them. There's probably, that's what I'm thinking, a limit to how fast you can make them as well, because they are not abstract mathematical entities. They are concrete physical objects. So obviously there is a Wikipedia page that lists the fastest computers known for different years, right? There's no point starting the list in the beginning because until 1961, they were listing it in a different kind of unit that I don't know how to compare. So we are going to start with this computer whose speed is measured in megaflops. Whatever a flop is, a megaflop is a million of those. And then as you go down the list, eventually it turns into gigaflops, which is instead of 10 to the power of 6 is 10 to the power of 9. So do be careful with that as you type these numbers into a spreadsheet. But after I did that, here is the result that I got. And it is beautiful. The speed of computers doesn't seem to be slowing down at all. This last one is 2023, okay? It's very recent. So if this is going to be logistic in the end, we're still not seeing it. You can try to model this data set exponentially. You can try to model it logistically. I'm not going to do this in the video because I'm going to leave it as an exercise for you. But what I'm seeing in the picture is that these guys and these guys are breaking the pattern, in my opinion. So the pattern that I see starts, it's not a horizontal because I looked at the numbers and I know that they are steadily growing, but this is what exponential does, right? It starts growing faster and faster so that everything else looks the same because it's squished. So it looks like it's close to zero, but this is 10 to the 11. So that's not zero. But after here, it doesn't seem to be growing exponentially anymore. This part is looking too much like a straight line for me to think it's exponential. Exponential after here would go here, something like that. So what I think is that if you take out these two and these two data points from the data set, consider them as outliers, and then try to model everything else logistically, then you get a picture that looks like this. I think that this is going to be a very good logistic regression, but I haven't done it. That's your exercise. And with that regression, you can predict how fast is the limitation, the fastest computer there can ever be. And also you can predict how long it's going to take for us to have it. So what I think is happening here is that the limitation we are seeing is of a certain type of technology. I'm betting after 2020, these and these were made in maybe a completely different way than they were being done before. It's not just a gradual increase in efficiency. I'm sure that Wikipedia page covers all of this, but I haven't read it. So if you want to do that, if you're curious, come back and tell me what you find, I guess. Show me your logistic regressions, and also come up with some other situations that you think would be good to model with a logistic function, something that needs to have two asymptotes. In the case of the computers, I am assuming there is a high asymptote, but that's just my opinion. What is not an opinion is that the low asymptote is zero. You can't have a computer whose speed is negative. The same thing is true for the life expectancy. A lot of people would like to believe that with better medicine we can live forever, but that may not be the case. What is definitely the case is that the low asymptote is at zero because it's impossible to live for a negative number of years.